Welcome, ladies and gentlemen, to Integrated Math 2. In today's episode, we will be discussing tangent lines and circles to see how they are related to each other. And so we're going to do this resource page, and then we're going to see if they do, in fact, have a relationship. So let's consider this circle, x squared plus y squared equals 25. We're going to identify the center and the radius of the circle. Hopefully it won't be that hard. If you look at the center, nothing's happening to x nor y, so I'm hoping that 0, 0 is the center of that circle. The radius, with r squared being 25, the radius ends up being 5. And it does say graph the circle in the space on the right. Now, I did want to have a certain amount of precision, so I went to Desmos and actually graphed a circle. That way it would appear to be more circular than not. So there's our circle with a radius of 5. Notice how it is centered at 0, 0, extends out 5 in each direction. So now let's go and write some lines that are passing through this circle here. So I'm going to go and find the slope of the line that passes through 3, 4 and negative 5, 10. So let's see, 3, 4, so 1, 2, 3, up 1, 2, 3, 4. That's going to be right here. And negative 5, 10 is going to be right here. And if I slope this thing down and have it pass through that point, what you'll notice is that the line hits the circle in a very peculiar kind of way. So I want you just to keep that in your back pocket, because we'll graph another line in just a second that will allow us to see a similar effect happen. But let's find the slope here. So if I make this x1 and y1 and x2 and y2, this will be using our formula to find slope, which is y2 minus y1 over x2 minus x1. That's going to be 10 minus 4 over negative 5 minus 3, which is going to be 6 over negative 8, which reduces to negative 3/4. That's our slope right there. Okay, so again, we'll just take a look at that slope. Keep it in our back pocket here. This is our slope. Awesome. All right, let me come back with the next part of the problem here. I'll be right back. And next thing we're going to do is we're going to find the slope of a second line passing through negative 4, 3 and negative 7, 1. So let's go and just find out that slope, and then we'll actually graph that line here. So why don't I go ahead and do it in a different color here. I'll go ahead and do it in purple. Hopefully it stands out enough against the circle. It's kind of purplish. I'll go ahead and do it in green. And so from here, again, we'll do y2 minus y1 over x2 minus x1, where this is x1, y1, x2, y2. So that's going to be negative 1 minus 3 over, looks like negative 7 minus negative 4. So what's negative 1 minus 3? Well, that's going to be negative 4 over, that's going to be negative 3, because that'll be negative 7 plus 4, which the slope ends up being 4/3, which actually shouldn't be too surprising. I mean, we're looking at a similar kind of point here if you look at 3, 4 and negative 4, 3. But I'll go ahead and draw that out real quick here. Negative 1, 2, 3, negative 1, 2, 3, 4, up 1, 2, 3. That's going to be right here. And if it passes through negative 7, negative 1, that's negative 5, negative 6, negative 7, negative 1. And if I go ahead and connect these two, let me go and scroll up a little bit more. If I connect these two, notice what happens with how they touch the circle, right? And so that's going to look kind of like that. Okay, so now let's answer some questions here. What are some things, actually I'll write down the slope right here, 4/3. So what do we notice about the two lines? How do they interact with the circle? Well, these two lines, the two lines interact with the circle by passing the circle, just touching it once. Now, when we studied systems of equations, we actually saw this effect happen. Sometimes we had a line that only touched the parabola once, or in this case, we have a line that only touches the circle once and passes right over it. This effect is what is known as a tangent line. In fact, the name of the lesson. And so a tangent line is defined. I'm going to do it down here in yellow. A tangent line is defined as a line that just touches a curve or function once. Now, there are actually there are a lot of other consequences that come with tangent lines, but that won't be coming up until a couple math classes in the future. But for now, you just have to know that a tangent line is a line that touches the curve or function only once. Again, like we saw it in the quadratic systems, we are seeing it now. But we're going to see what kind of relationship a tangent line has with a circle, and we're going to see that in the next couple minutes here. Let me get the next set of problems that accompany this resource page here. I'll be right back. So it asks, what is the relationship between tangent lines and circles? And it says, in the previous two lines we just graphed, identify their slope. So the slope of the first line, again, this blue line here, was negative 3/4. And so we'll go and write that down here. Negative, oops, gotta change colors there. Negative 3/4. And the slope of line 2 ended up being 4/3. I apologize, I did delete that part of the problem, but if you want, you just go back and take a look at what that slope actually was. Now what we're going to do is we're going to find the slopes of the radii to their respective points of tangency. So from here, the point of tangency is where the line touches the curve. So at this point, the point of tangency would be considered 3, 4. Hopefully that makes sense to you. That would go to the right 3 and up by 4. This point of tangency would be back 4 up 3, so negative 4, 3 would be the point of tangency. And so let's go and find what the slopes of the radii are. So from here, from 0, right, because that's the center of my circle, I'm going to go up to here. And I'll go and just draw that slope triangle. Well, what is the slope of this triangle right here? Well, that's going to be 4 up and 3 to the right. And so let's see. We're going to go up 4 to the right by 3. And then this one here, this radius's slope, looks like I had to move, looks like to the left by 4 and up by 3. So that's going to be negative 3/4 here. So negative 3/4. And so what we have to notice, what we're trying to get you to notice is the relationship between the slope of the tangent line and the slope of the radius at the point of tangency. So let's consider slope of line 1 versus the slope of radius 1. Well, that's going to be negative 3/4 versus 4/3. The other one is going to be 4/3 versus negative 3/4. Now, hopefully the slope relationship will make sense to you, because if we multiply each of them together, we'll end up with negative 1. Well, what is the relationship between two slopes who, when you multiply them together, they get negative 1? In other words, one is one thing and the other is the opposite sign reciprocal. The relationship we're trying to get you to see here is that the slopes are perpendicular. The slopes are perpendicular to each other. They form a 90-degree angle every single time. So what happens is, if I was to draw this in a different color here, I'll go ahead and do it in orange. This radius and this slope create a 90-degree angle like that, and this radius and this slope create a 90-degree angle like that. So that is the big takeaway from this, is that the slopes are perpendicular. But it doesn't quite answer the question, like, why do we call tangent lines tangent? And then the last question on this page, which asks kind of a weird question. So I'll be back with that one. Give me a second. What's always interesting is how tangent came to have its name. And, we first learned that tangent, back in this class, we learned that tangent was known as the ratio of the opposite side to the adjacent side. And now we know it's also used to describe a line that touches a curve at one point. And so this is just one of the ways that tangent has kind of received its name. But let's find out how the two are related, the notion of tangent line versus opposite over adjacent. Look at this circle to the right, which has a radius of 1. I'm going to start by drawing a line, x equals 1, which is going to be a vertical line. I'll go ahead and draw it in blue here so it kind of stands out real quick here. So I'm going to go ahead and draw, oops, darn it. Whoa, that was disgusting. Let's see, there we go. That's what I'm talking about. Right there, there's my tangent line. In fact, I'll even make it just a little bit thicker. That way we can really, get that verticality of this thing going. And let me shrink the pen size just a little bit. Back to, there we go. Awesome. So this is the line x equals 1, right? But I'll go ahead and give the name, the line a name here in just a second here. And so what I'm also going to do is now, was I've noticed that the line is tangent to the circle, right? It touches only 1 point. From 0, 0, I'm going to draw the line y equals x that crosses the line x equals 1. It doesn't really matter what the slope is, but I figured y equals x is something that's pretty easy to understand. It just has a slope of 1, so I'll go ahead and just draw it. And in fact, I'm going to make the pen just a little bit thicker. I feel like on this, it needs to be just a bit thicker. That way people can see what I'm doing here. There we go. There we go. Nice and thick line. Boom. So there we go. We've got an intersection right there. And so now it says where y equals x crosses the circle, draw another vertical line down. So I'm talking about right here. And I'm going to go and just draw another vertical line down here. And what two shapes have just been created? Well, it looks like the orange is a right triangle. But if you look at it from another perspective here, you could almost see, if I just kind of barely highlight out, there's another right triangle at play, right? There's the outer blue right triangle, and then there's the inner orange right triangle. Hopefully we can all see that. So let's write that down in our notes here. We have just created two right triangles. Now, the inner angle here, I'll go and put it in black real quick here. I'll go and call this inner angle theta, okay? And then I will come back and I will get the next part of the problem. Give me a second. Whoops. Okay, so step 4 tells me to label the inner right triangle. I've got to label its horizontal and vertical directions and then label the acute angle at the origin. We have to compare the two triangles. Okay, so it's a lot taken, but basically what I'm being asked to do here is I'm being asked to draw two triangles here and see how they're related. So the first triangle, right, I'll call, oops, why don't I just keep it color-coded? The orange inner triangle. The orange inner triangle, like that, okay? And then there's the blue outer triangle, which is definitely larger. Well, from here, I'm going to label the angles again. Now, I'm hoping you guys are seeing where this is going. This is theta and this is theta, and they're both 90-degree angles. I'm hoping you're starting to see a relationship between the two triangles here. Well, considering this this thing is, you know, going out this far, I could call it a number, but instead, since I want to be able to scale up and scale down a circle at will, and since all circles are similar, I'll just go and call the bottom side, I'll just call them some value of x. Some value of x, right? It doesn't really matter how big it is, you know, because I could enlarge in the circle and it'd be larger. I could shrink the circle, it would be smaller, but it's just going to be some value of x, right? And I know that because I had to go some value of x out. You know, it's not really defined how much. But this side here will be y, right? I mean, that's just some value of y. Again, the bigger the circle, the bigger the triangle. But I just want to make sure that it's just some generic, general term. The blue triangle, however, is a little more specific because if you notice the circle, it has a radius of 1, right? So if I was to draw this out right here like this, and actually make contact with the vertical side, that side is very much defined. It's not just x, I'm going to call it 1. Now from here, you know, I don't have a name for this line. I don't want to call it 1 because it's definitely not the same measure as the other one. But it is a tangent line, so I'll go ahead and just call it tangent. And I'll go ahead and just call it tangent of the angle theta. Because, you know, at this point we know we put angles inside of tangent, sine, and cosine. But we'll go ahead and just call it tangent of theta. Now at this point, I'm hoping you guys can see the relationship between the two triangles and that they are similar. Where now I'll go ahead and do, looks like y over tan theta, right? So vertical side to vertical side is equal to x over 1. And if I go and cross multiply those, I'm going to get x times tangent of theta equals y, divide both sides by x, and I get tangent, oops, that's bad handwriting, tangent of theta equaling y over x. And if you look at the relationship of the y to the x and the angle, it is the opposite over the adjacent side. So that's how we get the opposite over adjacent relationship to tangent. So that's just one way to show how tangent kind of got its name. I hope you found that interesting. But from here, I'm hoping you guys just understand that tangent lines to circles, the radii and the slopes of the tangent lines are perpendicular. That is what we want you to get out of this lesson. So as long as you understand that, then you'll be in good shape. And yeah, I think that'll do it for this lesson. So as always, please leave comments or questions in the comments area, and I will see you all in the next episode.